February 20th, 1943, north of Kasserine Pass, Tunisia. Oberleutnant Hans Richter crouches in an abandoned American foxhole, his gloved hands wrapped around what appears to be nothing more than a simple steel tube. 13 pounds of crude metal piping with wooden furniture attached. No complex recoil mechanism. No precision optics. Just basic iron sights and an electrical trigger that looks like it belongs on a child's toy. For 7 years, German engineers had perfected anti-tank warfare through mathematical precision. The Pak-40 anti-tank gun weighed 3,100 pounds and required 6 trained specialists 20 minutes to position for combat. When Soviet 34s appeared with their sloped armour, the German response was predictable. Build bigger guns, heavier systems, more sophisticated fire control mechanisms. This American contraption looks like something a plumber assembled in his basement workshop on a Sunday afternoon. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Richter slides his fingers along the manufacturer's stamp. General Electric, Bridgeport, Connecticut. The same Americans who build refrigerators and washing machines apparently think they can design anti-tank weapons. The absurdity would be laughable if Wehrmacht intelligence hadn't specifically ordered all captured examples shipped immediately to testing facilities in Germany. 3 days later, at the Kummersdorf proving grounds outside Berlin, Hauptmann Werner Gruber examines the captured launcher with the contempt of a Prussian officer confronted with amateur engineering. 42 years old, 2 decades of military service, veteran of the Great War's artillery campaigns, Gruber has built his reputation on systematic evaluation of weapons that conform to German standards of precision and complexity. This American device violates every principle he holds sacred about proper military equipment. Launcher, rocket, anti-tank, 2.36-inch, Monet. Technical markings. His voice carrying the dismissive tone of someone who has already reached his conclusion. Americans excel at mass production of consumer goods, automobiles, radios, kitchen appliances, but precision anti-tank weaponry requires engineering sophistication that American industry has never demonstrated. The weapon's very crudeness seems to confirm every assumption about American technical incompetence. Simple welded seams where German weapons would require precision machining. Heavy steel construction where proper engineering would use lighter alloys. Electrical firing systems where German doctrine demands reliable mechanical percussion caps. Everything about the bazooka suggests industrial shortcuts rather than military effectiveness. But when they load the first captured M6 rocket and fire at a British Crusader tank positioned 50 meters downrange, the shaped charge warhead punches clean through 40 millimeters of armor plate, with a sharp crack that echoes across the testing grounds. The penetration is complete, decisive, and utterly impossible, according to everything German engineers believe about portable anti-tank warfare. The room falls silent. Gruber stares at the smoking hole in the Crusader's frontal armor, his mind struggling to reconcile empirical evidence with doctrinal assumptions. The numbers don't lie. This primitive American tube just delivered battlefield-decisive firepower with the weight and complexity of a hunting rifle. Everything German anti-tank doctrine is built upon has just been proven wrong by a device that appears to have been designed by enthusiastic amateurs rather than professional engineers. The morning sun cast long shadows across Kasserine Pass as Richter picked his way through abandoned American positions on February 21st. The rocky Tunisian terrain still carried the acrid smell of cordite and diesel fuel from the previous day's engagement. Scattered equipment told stories of hasty withdrawal, torn maps, abandoned ration tins, a single combat boot with its laces still tied. But it was the metallic glint from a foxhole that caught Richter's attention, drawing him toward what would become one of the war's most significant intelligence finds. The device measured roughly 137 centimeters from end to end, simple steel tubing with minimal external components. A wooden shoulder stock attached to one end, basic iron sights that wouldn't look out of place on a civilian hunting rifle. The entire assembly weighed perhaps 13 pounds, less than a single round of ammunition for Germany's standard 7.5-centimetre Pak-40 anti-tank gun. Richter's engineering background, 12 years at Krupp Works before the war, allowed him to recognize sophisticated simplicity when he saw it. This American launcher represented either brilliant minimalism or catastrophic design failure. German anti-tank systems embodied precision engineering philosophy, where complexity and effectiveness were considered synonymous. Every Wehrmacht weapon system required teams of specialists, careful maintenance, and mathematical calculation before firing. This American device looked like something that could be operated by soldiers with minimal training. The contrast couldn't have been starker with German equipment doctrine. The Panzerschreck 39 anti-tank rifle weighed 27 pounds and required 2 soldiers for effective operation. The Pak-38 towed gun weighed 2,170 pounds and needed a truck for battlefield mobility. Even Germany's newest development, the Panzerfaust, demanded careful handling and specific range estimation before firing. American engineers had apparently decided that anti-tank weapons should be simple enough for any infantryman to operate without extensive training or complex calculations. Richter carefully lifted the tube, noting its crude but functional construction. No, delicate, and optical equipment that might be damaged by rough handling. No precision ground surfaces requiring careful maintenance. No sophisticated recoil mechanisms with tight tolerances. The firing system appeared to consist of nothing more than a battery, basic wiring, and simple electrical contacts. Everything about the weapon violated fundamental principles of German military engineering, where sophistication was considered proof of effectiveness. 2 other American launchers were discovered in nearby positions that afternoon, along with 7 rockets still in their fiber shipping tubes. Wehrmacht intelligence procedures demanded immediate documentation and transport to German testing facilities. Within 72 hours, all 3 captured bazookas and their ammunition were aboard a Ju-52 transport aircraft heading for Kummersdorf proving grounds. At Kummersdorf, Hauptmann Gruber commanded the Wehrmacht's primary weapons testing facility with the methodical precision that characterized German military bureaucracy. The proving grounds sprawled across 2,000 hectares of Brandenburg countryside, equipped with firing ranges, impact zones, and technical laboratories, where every new weapon system underwent rigorous evaluation before field deployment. Gruber's testing protocols were legendary throughout the Wehrmacht for their thoroughness and objectivity. No weapon received approval without comprehensive performance data. No system entered production without meeting exacting German standards. His evaluation reports had rejected equipment from Germany's finest manufacturers when specifications failed to meet military requirements. The captured American bazooka arrived on February 24th, with intelligence reports suggesting the weapon represented a significant development in portable anti-tank capability. Gruber read these assessments with skepticism born from 2 decades, evaluating weapons that rarely lived up to their designers' claims. Americans produced excellent radios and reliable trucks. Their industrial capacity for mass production was undeniable. But precision military equipment required engineering sophistication that American consumer goods manufacturers had never demonstrated. Oberfeldwebel Ernst Koch, Gruber's senior testing supervisor, unpacked the captured launchers with the careful attention of someone who had handled thousands of weapons during his 15-year career at Kummersdorf. The American devices felt surprisingly lightweight in his experienced hands. Crude welding along the seams, heavy-gauge steel that proper engineering could have lightened by 30%, wooden furniture that would absorb moisture and warp in field conditions. The electrical firing system particularly troubled Koch. German weapons used mechanical percussion systems with carefully calibrated spring tensions and precisely machined firing pins. Americans had apparently replaced proven mechanical reliability with electrical components that could fail from moisture, temperature extremes, or simple battery depletion. The system seemed designed for convenience rather than battlefield durability, but Koch had learned through years of weapons testing that assumptions meant nothing compared to empirical evidence. Performance data would tell the truth regardless of preconceptions about American engineering competence. The first test series began on February 26th under clear winter skies. Gruber had positioned a captured British Crusader tank at 50 meters, standard engagement range for German anti-tank weapons. The tank's 40mm frontal armor represented typical protection for Allied medium armor. German Pak-38 guns could penetrate this thickness at 500 meters. The Pak-40 could defeat it at 1,000 meters, but those weapons weighed over a ton each and required trained crews and truck transport. This American launcher weighed 13 pounds and could be carried by a single soldier. The contrast embodied fundamental differences in anti-tank philosophy. German doctrine concentrated firepower in heavy, precise systems operated by specialists. American approach apparently emphasized distributing anti-tank capability to individual infantry units regardless of technical complexity. Unteroffizier Klaus Weber, selected to operate the captured launcher, had 12 years of artillery experience and 4 months of anti-tank training. He shouldered the American tube with casual familiarity that belied his nervousness about firing a weapon he barely understood. No complex sight picture, no precise range calculation, no consideration of wind or target angle. American instructions captured with the weapon suggested simply aiming center mass and firing. The simplicity seemed almost insulting to someone trained in proper German gunnery procedures. Weber squeezed the electrical trigger. The rocket motor ignited with a sharp whoosh, propelling the M6 warhead, downrange in a streak of smoke and flame. 0.8 seconds of flight time. The shaped charge struck the Crusader's frontal armor with a crack that echoed across the proving grounds. Instead of bouncing harmlessly off the steel plate as German expectations suggested, the explosion punched a clean hole through 40 millimeters of armor. The penetration was complete and devastating. Superheated metal jet had carved through the tank's protection, as if the armor plate were nothing more than sheet metal. The silence that followed lasted nearly 30 seconds. Koch stared at his observation instruments, checking and rechecking measurements that seemed impossible. Gruber's face had gone pale, his Prussian composure shattered by empirical evidence that contradicted 2 decades of professional experience. This primitive American tube had just delivered battlefield decisive anti-tank capability with the operational simplicity of a rifle. Every assumption underlying German weapons doctrine had been proven wrong by a device that looked like it had been designed by amateur enthusiasts rather than professional military engineers. "Prepare another rocket," Gruber ordered quietly, his voice carefully controlled. "I need to see that again." The memory came unbidden to Koch as he stared at the smoking hole in the Crusader's armor. August 1941, when intelligence photographs first arrived from the Eastern Front showing German 3.7 centimeter anti-tank shells bouncing harmlessly off Soviet 34 tanks. The Pak-36, which had effortlessly destroyed Polish and French armor in 1939 and 1940, had become obsolete overnight against 45 millimeters of properly sloped Soviet steel. Germany's response had been characteristically methodical and devastating. Within 6 months, Krupp engineers developed the 5-centimeter Pak-38, weighing 2,170 pounds and capable of penetrating 61 millimeters of armor at 500 meters. When that proved insufficient against improving Soviet tank designs, German engineers scaled up again. The 7.5-centimeter Pak-40 at 3,100 pounds. Then the monstrous 8.8-centimeter Pak-43 weighing nearly 10,000 pounds with its gun carriage and equipment. Each solution represented mathematical elegance translated into steel and precision machinery. Each system required specialized crews, careful positioning, and substantial logistical support. The Pak-40 demanded 5 trained specialists for operation and 20 minutes for proper combat deployment. Ammunition weighed 60 pounds per round. Theoretical maximum rate of fire reached 14 rounds per minute under perfect laboratory conditions. In actual combat, considering target acquisition, range calculation, and crew coordination, Effective firing rates rarely exceeded 6 rounds per minute. But Soviet tank production had reached 1,534s monthly by late 1942. German towed anti-tank guns, regardless of their mathematical perfection, simply couldn't be everywhere simultaneously. Each Pak-40 represented thousands of man-hours of precision manufacturing, specialized steel alloys, and trained personnel. Resources that Germany was rapidly exhausting across multiple fronts, stretching from North Africa to the Arctic Circle. Koch had participated in Pak-40 evaluations, contributing ballistic analysis and armor penetration calculations. The engineering was flawless, the manufacturing tolerances precise to fractions of millimeters. German anti-tank doctrine assumed that superior weapons technology would overcome numerical disadvantages through technical supremacy. Quality over quantity remained the fundamental principle underlying all Wehrmacht equipment development. Now, studying this crude American tube, Koch began understanding revolutionary implications that German doctrine had never considered. The bazooka weighed 13 pounds compared to the Pak-40's 3,100 pounds, a weight advantage of 238 to 1. Crew requirements: 1 operator plus 1 loader versus 6 trained specialists. Setup time: 15 seconds versus 20 minutes. Transportation: man-portable versus truck-dependent. Most significantly, training requirements told a story that made Koch's artillery background recoil with implications. Captured American technical manuals suggested 2 hours of instruction for basic bazooka proficiency. German anti-tank gun crews required 200 hours of training before combat deployment. American approach violated every principle German weapons philosophy held sacred, yet delivered 90% of German anti-tank effectiveness at 1% of the weight, complexity, and manufacturing investment. The revelation was devastating. Americans hadn't asked how to build the most effective anti-tank gun. They had asked how to give every infantry squad anti-tank capability. The difference in fundamental questions had produced radically different solutions that challenged German military thinking at its philosophical core. Gruber stood beside the punctured crusader, his engineering pride wrestling with empirical evidence that couldn't be dismissed or rationalized. The shaped charge had performed exactly as demonstrated, punching through British armor with casual efficiency that made German precision seem almost quaint by comparison. This wasn't sophisticated ballistics requiring complex calculations. It was applied physics, reduced to elementary components, packaged for mass production, and distributed to soldiers who required minimal training. "Run comprehensive penetration tests," Gruber finally ordered, his voice carefully neutral. 20 millimeters through 60 millimeters at ranges from 25 to 100 meters. I want complete documentation before filing preliminary reports with Heereswaffenamt. Koch recognized defensive bureaucratic maneuvering when he saw it. Gruber needed irrefutable data before admitting to Wehrmacht High Command that American amateurs had solved portable anti-tank warfare more effectively than Germany's finest weapons engineers. The systematic testing would take weeks, providing time to process philosophical implications of what they were discovering about American industrial thinking. Over the following days, Koch assisted in establishing rigorous test protocols with mathematical precision that characterized German military evaluation procedures. 50 rockets were allocated for systematic trials. Accuracy measurements recorded to the nearest centimeter. Penetration depths calculated using precision instruments measuring entry and exit wounds in test armor plates. Environmental conditions documented for every firing sequence. The results formed an undeniable pattern that grew more disturbing with each data point collected. At 50 meters, the bazooka achieved 78% accuracy against tank-sized targets. Penetration remained consistent across varying armor thicknesses, with the shaped charge warhead defeating 60 millimeters of steel plate at all tested combat ranges. Reliability under field conditions, including exposure to temperature variations and rough handling that would disable German optical equipment, maintained a 94% successful ignition rate. Most troubling was the weapon's resistance to abuse. German precision instruments required careful maintenance and environmental protection. The American bazooka functioned normally after being dropped from vehicle heights, exposed to moisture, and subjected to temperature swings that would compromise German firing mechanisms. The electrical system proved more robust than German percussion cap mechanisms, requiring neither precise adjustment nor specialized maintenance procedures. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Koch compiled findings into systematic engineering analysis, but conclusions remained unavoidable. American industrial philosophy had produced superior battlefield results by accepting limitations German engineers refused to consider. Traditional metrics of anti-tank effectiveness, SSA, range, precision, maximum penetration, MIOT, had been sacrificed to optimize variables. German doctrine considered irrelevant portability, simplicity, mass production capability, and ease of training. The Americans had been strategically correct. German engineers had been tactically precise, but strategically wrong about which variables mattered most in total warfare, where equipment availability often determined outcomes more than individual weapon performance. Gruber's systematic evaluation program continued through March, with methodical precision that characterized all German military testing protocols. Koch prepared 3 distinct test series, each designed to quantify specific performance parameters under controlled, scientific conditions. 17 captured M6 warheads would be expended according to carefully structured experimental procedures that would either validate or debunk the weapon's apparent capabilities. Test Series Alpha focused on penetration characteristics across varying armor thicknesses. Koch procured steel plates ranging from 20 mm to 60 mm, representative of armor found on everything from reconnaissance vehicles to main battle tanks. Each plate was positioned at precisely measured distances, 25, 50, 75, and 100 meters from the firing position. Temperature, humidity, wind speed, and barometric pressure were recorded for each trial. German thoroughness demanded that every variable be documented and controlled. The first rocket struck a 20 mm plate at 25 meters with devastating effectiveness. The shaped charge warhead punched through the steel with such violence that the exit hole showed clean, almost surgical edges. Evidence of the Monroe effect, creating a superheated jet of metal traveling at hypersonic velocity. Koch measured the penetration hole at 62 mm diameter, surrounded by minimal spalling or secondary damage. The American warhead had converted its 3.4 pounds of explosive into focused energy, with remarkable efficiency that exceeded theoretical expectations. Successive trials against thicker armor produced equally disturbing results. 40 mm plates, standard frontal protection for German Panzer III tanks, offered no meaningful resistance. The shaped charge effect appeared essentially independent of armor thickness within tested ranges, defeating 60 mm plates with the same casual efficiency demonstrated against lighter protection. Koch recorded penetration performance that exceeded German Panzerfaust prototypes, still under development at Rheinmetall facilities. The implications were staggering for German anti-tank doctrine, that had always emphasized bigger guns firing heavier projectiles at higher velocities. Test Series Beta examined accuracy characteristics under simulated combat conditions. 30 rockets were allocated for systematic firing trials against tank-sized silhouettes at 100-meter ranges. Each shot was fired by different operators, German soldiers trained according to captured American instruction manuals, TUL, to eliminate individual shooter variables from performance data. The results challenged fundamental assumptions about precision weaponry that had dominated German military thinking for decades. 78% of rounds impacted within designated target zones, an accuracy rate that compared favorably to German-towed anti-tank guns operated by veteran crews with years of training. The American weapon achieved this performance using soldiers with less than 4 hours of instruction, firing from unsupported positions without optical range-finding equipment or complex. Ballistic calculations. The simplistic iron sights and elementary aiming procedure delivered battlefield-effective precision through what German engineers could only describe as intuitive design philosophy that prioritized operator simplicity over technical sophistication. More significantly, accuracy remained consistent across different operators, regardless of military background or technical education. Experienced artillerymen performed marginally better than infantry riflemen, but both groups achieved hit rates that would satisfy combat requirements. The weapon's inherent simplicity eliminated specialized training bottlenecks that limited German anti-tank gun deployment to carefully selected personnel with extensive technical instruction. Test Series Gamma evaluated reliability under field conditions approximating North African combat environments where the weapon had been captured. Remaining rockets were subjected to temperature extremes, sand infiltration, rough handling, and simulated combat stress before firing. Desert heat reaching 48 degrees Celsius. Sand particles deliberately forced into electrical firing mechanisms. Intentional mishandling designed to simulate battlefield conditions that routinely disabled German precision instruments. 94% successful ignition rate. The statistic made Koch physically uncomfortable as he recorded the data in his evaluation logs. German percussion firing systems, with their precisely machined components and carefully calibrated spring tensions, rarely achieved such reliability under laboratory conditions, let alone after deliberate abuse designed to induce failures. The American electrical system, IMN, simple battery, basic wiring, robust contact points, 10C, proved more resilient than sophisticated German mechanisms requiring regular maintenance and environmental protection from moisture and temperature variations. Engineer Klaus Hoffmann arrived from Rheinmetall during the final week of testing, temporarily assigned to assess manufacturing implications of the American design. Hoffmann's production management background provided crucial perspective on industrial philosophy underlying the Bazooka's construction. Where Koch saw engineering principles, Hoffmann recognized manufacturing strategy that prioritized mass production over individual unit optimization. "Look at these tolerances," Hoffmann muttered, examining the launch tube's internal dimensions with precision measuring instruments. American manufacturing accepts variance ranges that would be rejected at any German facility, yet the weapon functions normally across the entire tolerance band. They designed for production capability rather than theoretical perfection. The aluminum launch tube showed tool marks and surface irregularities that would never pass German quality control inspection. But these apparent defects had zero impact on weapon performance. American engineers had identified which specifications actually mattered for battlefield effectiveness, then deliberately ignored everything else to enable rapid manufacturing. The result was a weapon system optimized for mass production by semi-skilled workers using standard industrial machinery rather than specialized equipment and master craftsmen. Hoffmann's cost analysis provided the final piece of Koch's growing understanding about American industrial philosophy. Captured procurement documents indicated material costs of approximately $11 per bazooka, with final unit pricing, including profit margins, reaching $18. German equivalent systems, even theoretical designs that might match bazooka performance, would require specialized steel alloys, precision machining, and skilled assembly procedures that would multiply costs by factors of 10 or more. They're building adequate weapons in enormous quantities, Hoffmann concluded during his briefing to Gruber and the testing staff. We're building perfect weapons in limited numbers. In total warfare, their approach wins through simple mathematics. Availability multiplied by acceptability equals battlefield effectiveness. Superior individual performance becomes irrelevant if you can't produce enough units to equip fighting forces. As March testing concluded, Koch compiled comprehensive performance data that would force Wehrmacht High Command to confront uncomfortable realities about German weapons development philosophy that had guided military procurement since the Great War. Every metric told the same fundamental story. American industrial thinking had produced superior tactical results by optimizing different variables than German engineers considered important or even relevant to weapon effectiveness. The numbers formed an undeniable pattern that challenged decades of Teutonic technical superiority assumptions built into every aspect of German military doctrine. Koch's final report contained one paragraph that captured the paradigm shift the bazooka represented for anti-tank warfare and weapons development philosophy. American engineers solved a problem German doctrine never recognized existed. While German anti-tank development focused on defeating specific armor thicknesses at maximum range with mathematical precision, American development focused on providing every infantry unit with immediate anti-tank capability, regardless of range or precision limitations. They optimized for tactical availability rather than technical superiority. The admission would sting German engineering pride, but empirical evidence demanded intellectual honesty. Within 48 hours of Koch's final test report reaching Heereswaffenamt headquarters in Berlin, Wehrmacht Ordnance issued Emergency Development Order 7743, immediate reverse engineering of captured American rocket launcher technology for German production. The directive acknowledged implicitly what no German officer would state explicitly: American amateurs had revolutionized portable anti-tank warfare using design philosophy that violated every principle German engineering held sacred. German engineers, their professional pride wounded but their pragmatism intact, began systematic analysis of every component, measurement, and manufacturing technique employed in the bazooka's construction. But ingrained German engineering culture demanded improvements, optimization, scaling, precision enhancements that would transform American simplicity into Teutonic complexity that better reflected German technical capabilities and military traditions. The design team at Rheinmetall Borsig, led by Diplom-Ingenieur Heinrich Langweiler, faced their first fundamental decision within days of receiving development orders. American bazookas fired 60mm rockets, delivering adequate penetration against most battlefield targets. German engineers immediately recognized opportunity for improvement through increased caliber that would provide superior armor, defeat capability. 88mm, matching the caliber of existing RPZB-GR 4312 warheads already designed for experimental Raketenwerfer 43 systems under development. Larger diameter meant greater explosive capacity, deeper penetration, more devastating terminal effects against heavy armor. The logic seemed irrefutable to German engineers trained to maximize individual weapon performance. Hoffmann watched the engineering discussions with growing concern born from his manufacturing experience. Each German improvement introduced complexity that compromised the bazooka's essential elegance and operational simplicity. The 88mm rocket motor required longer burn duration to achieve comparable muzzle velocity, extending flame projection well beyond the launch tube's protective confines. American 60mm rockets burned completely within their launchers, eliminating backblast hazards for operators. German 88mm rockets would continue burning for 2 additional meters after leaving the tube, creating safety requirements that didn't exist with American designs. Protective equipment will be mandatory, Langweiler announced during April design reviews at Rheinmetall headquarters. Gas masks, protective gloves, flame-resistant ponchos. The larger rocket motor creates operational safety requirements that American operators don't face, but the increased armor penetration justifies these additional complications. Hoffmann recognized the familiar pattern emerging again. German thoroughness creating operational complications that American simplicity had avoided through accepting performance limitations. The larger warhead would deliver superior battlefield performance against heavy tanks, but would transform a weapon any soldier could operate into a system requiring specialized training and equipment that limited tactical flexibility. German improvements were simultaneously making the weapon more effective against armor and less practical for infantry operations, requiring rapid displacement and tactical flexibility. Manufacturing specifications revealed deeper philosophical differences between American and German industrial approaches that extended far beyond simple design choices. The bazooka employed simple steel tubing with basic dimensional tolerances that accommodated normal manufacturing variations without compromising function. German engineers demanded precision bore dimensions calibrated to fractions of millimeters, ensuring optimal projectile alignment and consistent ballistic performance that reflected traditional standards of weapons manufacturing. The electrical firing system, crude but reliable in American hands, required complete redesign using German standard components that met Wehrmacht reliability specifications. Rheinmetall engineers couldn't accept simple American battery and wire configurations that violated German electrical standards established over decades of military equipment development. By June 1943, prototype Raketenpanzerbuchse 54 units were emerging from German factories, visibly superior weapons that embodied everything German engineering represented. 164 centimeters long compared to the bazooka's 137 centimeters. Weight: 9.25 kilograms empty versus the American weapon's 5.9 kilograms. The 88mm warhead delivered 100mm of armor penetration compared to the bazooka's 75mm, with effective range extended to 150 meters. Every specification represented measurable improvement over American design. Every improvement added weight, complexity, and manufacturing requirements that would limit production capacity. Hoffmann's production analysis provided sobering context for these technical achievements that German engineers celebrated as proof of superior design philosophy. German manufacturing, already strained by multi-front warfare and strategic bombing campaigns, struggled with the Panzerschreck's precision requirements that demanded specialized machinery and skilled labor, increasingly difficult to obtain. American bazookas utilized standard industrial steel tubing available from any competent manufacturer. Basic electronics that could be assembled by semi-skilled workers. Assembly procedures that required minimal specialized training or equipment. German versions demanded calibrated bore machining using precision equipment. Complex electrical systems incorporating Wehrmacht standard components with exact specifications. Specialized blast protection assemblies requiring skilled fabrication and quality control procedures. Early production rates reflected these manufacturing challenges in numbers that troubled Wehrmacht procurement officers. Rheinmetall facilities were producing approximately 400 Panzerschrecks monthly by August 1943, with plans to expand production to 8,000 units monthly by December through facility expansion and supplier contracts. Intelligence reports indicated American factories were already producing 30,000 bazookas monthly, with capacity expansion continuing across multiple manufacturing sites using converted automotive facilities. German precision engineering was being systematically overwhelmed by American mass production capability that treated weapons as industrial products rather than precision instruments requiring master craftsmanship. The broader implications troubled Hoffmann as he analyzed captured American technical documentation throughout the summer months. The bazooka represented more than anti-tank technology innovation. It embodied American industrial philosophy that prioritized adequate solutions produced in overwhelming quantities over perfect solutions produced in limited numbers through resource-intensive manufacturing processes. This same philosophy was appearing across American weapons development programs that German intelligence was beginning to document. Sherman tanks with adequate armor and reliable mechanical systems versus German Tigers with superior protection but chronic spare parts shortages and mechanical complexity. Monet-Garand rifles with acceptable accuracy and excellent reliability versus German Kar-98s with superior precision but slower rate of fire. Everywhere German engineers looked, Americans were accepting performance limitations to optimize for mass production, standardization, and logistical simplicity. Combat reports from Sicily and early Italian operations during summer 1943 provided empirical validation of German fears about American tactical flexibility. American bazooka teams were engaging German armor with mobility that traditional anti-tank guns could never match. Individual soldiers carrying 13-pound weapons could establish anti-tank positions in terrain inaccessible to German guns, requiring truck transportation and crew deployment. Setup time, measured in seconds rather than minutes, allowed American teams to engage targets and relocate before German counterfire could respond. Multiple bazooka teams could establish overlapping fields of fire that German doctrine had always assumed required towed gun positions with their inherent deployment limitations. More disturbing were reports of American industrial expansion specifically targeting rocket launcher production with the efficiency that characterized their entire war mobilization effort. Ford Motor Company had converted automobile assembly lines to bazooka manufacturing, achieving production rates that German planners considered impossible without specialized weapons facilities. General Electric was producing rocket motors using the same industrial techniques employed for radio manufacturing, applying consumer goods production expertise to military equipment with devastating effectiveness. American industry was demonstrating capabilities that German planning had never anticipated or prepared to counter through increased domestic production. By autumn 1943, German troops were carrying 88mm Panzerschrecks into combat against American bazookas, a direct technological lineage from captured enemy equipment to frontline German weapons. The irony wasn't lost on experienced Wehrmacht officers who understood they were fighting American designs with German improvements that made the weapons heavier, more complex, and harder to produce in necessary quantities. German engineers had learned from American simplicity, then inevitably complicated the solution through ingrained habits of precision engineering that couldn't accept adequate performance when superior performance seemed achievable through additional complexity. Combat effectiveness reports from November operations revealed practical consequences of German improvements that looked impressive on paper but created operational challenges in actual battlefield conditions. Panzerschreck teams achieved higher single-shot kill probabilities against Allied armor, with the larger 88mm warhead defeating heavier armor than American 60mm rockets could penetrate. German crews appreciated the increased lethality against targets like Sherman tanks with 75mm frontal armor. But the Panzerschreck required longer training periods to master safe operation procedures, specialized protective equipment that American bazooka teams didn't need, careful handling procedures that limited tactical flexibility in fast-moving combat situations where seconds often determined survival. American bazooka teams maintained higher operational availability through simplified maintenance requirements and reduced logistical support needs that allowed greater tactical independence. The weight difference became increasingly significant as combat reports accumulated through late 1943. The Panzerschreck's 20.3 pounds versus the bazooka's 13 pounds might seem trivial in garrison conditions. In actual combat, across difficult terrain, after hours of infantry movement, that additional 7 pounds represented decreased mobility that tactical commanders noticed immediately. German infantry squads equipped with Panzerschrecks moved more slowly than American units with bazookas, required more frequent rest stops during approach marches, struggled more with rapid position changes under fire. The weight penalty that German engineers had accepted to achieve superior armor penetration was creating tactical disadvantages that couldn't be measured in laboratory testing, but mattered enormously in actual combat operations. The final accounting arrived with December production statistics that painted a comprehensive picture of industrial competition between German precision and American mass production. German factories had achieved 8,000 Panzerschrecks monthly production by year-end, a remarkable industrial accomplishment under wartime conditions that included strategic bombing, resource shortages, and labor constraints. Engineers and production managers had overcome enormous obstacles to reach this output level that represented German industrial capability operating near maximum efficiency. American facilities were producing 37,000 bazookas monthly, with capacity still expanding through additional factory conversions and supplier contracts. German engineering superiority in individual weapon performance was being systematically overwhelmed by American manufacturing philosophy that treated weapons as industrial products to be mass-produced using standardized components and simplified assembly procedures. Hoffmann's year-end analysis captured the essential paradox that Wehrmacht leadership struggled to acknowledge. We have built a superior bazooka that outperforms the American original in armor penetration, range, and lethality. The Americans have built 400,000 adequate ones that equipped every infantry division and many supporting units with organic anti-tank capability. In total warfare, their approach wins through mathematics that no amount of individual weapon superiority can overcome. November 1943 brought the first comprehensive battlefield effectiveness analysis that would force German military leadership to confront uncomfortable truths about their engineering philosophy and its strategic implications. Koch, now assigned permanently to weapons development analysis at Oberkommando der Wehrmacht headquarters in Berlin, compiled after-action reports from across multiple theaters where German and American rocket launchers had engaged in direct technological competition. The statistical evidence painted a picture that challenged every assumption underlying German weapons development doctrine that had guided procurement decisions since the Great War. American bazooka performance data revealed 847 successful engagements against German armored vehicles across North African and Italian operations through November. More significantly, crew survivability rates reached 89%, a statistic directly attributable to the weapon's lightweight design, enabling rapid displacement after firing. German crews operating heavier, more complex Panzerschrecks struggled to achieve comparable mobility under enemy fire, with survivability rates reflecting this tactical disadvantage. Training requirements told an equally disturbing story about operational efficiency. American replacement crews achieved combat effectiveness after an average of 8 hours of instruction compared to 24 hours required for German Panzerschreck operators. The difference might seem minor until Wehrmacht training commands calculated total training burden across thousands of replacement crews needed to maintain frontline strength. American simplicity was reducing training overhead by 2/3 compared to German systems, requiring specialized instruction in safety procedures, blast protection, and handling requirements. The production cost analysis provided the most damaging evidence against German engineering approaches that prioritized individual weapon performance over manufacturing efficiency. American procurement documents captured during Italian operations indicated total production costs of $18 per bazooka unit through mass production techniques that utilized standard industrial components and simplified assembly. Procedures. German accounting for Panzerschreck manufacturing, including specialized tooling, precision machining, blast shield fabrication, and quality control procedures, exceeded 127 Reichsmarks per weapon. At official exchange rates, approximately $51 per unit. Nearly 3 times more expensive for capabilities that offered only marginal battlefield advantages over American designs in most tactical situations. German Panzerschreck performance statistics, while demonstrating superior individual weapon effectiveness, revealed systemic limitations that American mass production philosophy had anticipated and avoided through design choices that prioritized operational simplicity. 1,156 successful engagements against Allied armored vehicles represented impressive single-unit performance that validated German engineering improvements. But crew survivability dropped to 71% due to the weapon's greater weight, reducing mobility and the extended rocket motor burn, creating backblast hazards that didn't affect American bazooka operators. The larger caliber that German engineers had pursued for superior armor penetration was creating tactical complications that American designers had eliminated by accepting adequate performance rather than maximum lethality. Hoffmann's manufacturing analysis provided context that made German engineering achievements appear almost Pyrrhic in nature when viewed through the lens of total war industrial competition. Rheinmetall facilities had achieved remarkable production efficiency under wartime constraints, reaching 8,000 Panzerschrecks monthly by December 1943 through heroic efforts by engineers and workers operating under strategic bombing and resource shortages. but American industrial capacity had expanded to 37,000 bazookas monthly, with Ford Motor Company alone producing more rocket launchers than the entire German weapons industry could manufacture. American mass production techniques were overwhelming German precision manufacturing through sheer numerical superiority that reflected fundamentally different approaches to industrial warfare. The paradigm shift extended beyond anti-tank weapons into broader military equipment philosophy that German intelligence was documenting across all categories of American war production. Reports indicated American development of assault rifle concepts similar to Germany's Sturmgewehr 44, but with characteristic American emphasis on rapid production rather than German precision engineering. Where German designers demanded exact tolerances and specialized steel alloys, American engineers accepted looser manufacturing standards that enabled factory workers with minimal training to produce adequate weapons in overwhelming quantities. Similarly, American tank development reflected the same philosophical differences that had produced the bazooka breakthrough. Sherman tanks sacrificed German-style armor thickness and mechanical precision for reliability, maintainability, and mass production capability that allowed American industry to overwhelm German technical superiority through numerical advantage. Individual German Tiger tanks demonstrated superior battlefield performance in direct engagements, but American factories were producing 5 Shermans for every Tiger that emerged from German facilities. Quantity was revealing qualitative advantages that German engineering doctrine had failed to anticipate or prepare to counter. Koch's most difficult analysis involved examining captured American technical manuals that revealed the intellectual framework underlying their design, philosophy, and industrial approach. American engineers consistently asked different fundamental questions than their German counterparts when approaching weapons development challenges. Instead of asking how can we build the most effective anti-tank weapon, American development teams asked how can we provide anti-tank capability to every infantry squad in every division deployed globally. The difference in basic assumptions and design questions produced radically different solutions, optimized for different variables that reflected distinct national approaches to industrial warfare. German engineering excellence focused on maximizing individual weapon performance through precision manufacturing, complex mechanisms, and specialized training requirements that produced superior equipment operated by elite specialists. American industrial design optimized for battlefield availability through simplified construction, mass production capability, and minimal training requirements that distributed adequate capability throughout entire military formations. Both approaches achieved their intended objectives within their respective philosophical frameworks. But total warfare favored American methodology through mathematical advantages that German technical superiority could not overcome when fighting across multiple fronts against enemies with superior industrial capacity. The intellectual honesty that had made Koch valuable to Wehrmacht leadership now forced him to acknowledge painful conclusions about German military-industrial philosophy that had shaped procurement decisions for decades. His final report to OKW contained analysis that would become legendary among post-war weapons developers and military historians studying industrial aspects of the Second World War. The Americans have demonstrated that optimal engineering solutions are not necessarily superior battlefield solutions when strategic context includes industrial capacity and logistical constraints. Their bazooka sacrifices our traditional metrics, AT, maximum range, ultimate precision, theoretical penetration, ATA, to optimize variables we considered irrelevant to weapon effectiveness, portability, operational simplicity, mass production capability, and distribution to non-specialist troops. They asked different questions about the problem and received revolutionary answers that challenged our fundamental assumptions about weapons development. By early 1944, American industrial design philosophy was infiltrating German weapons development across multiple programs, as pragmatic engineers recognized that survival required adapting to strategic realities. The Sturmgewehr 44 assault rifle incorporated simplified manufacturing techniques that prioritized production volume over traditional German precision standards that were becoming impossible to maintain under wartime. Constraints. Panzerfaust disposable launchers embraced single-use simplicity over German preferences for reusable, maintainable weapon systems that required more resources to manufacture. Late-war tank designs increasingly emphasized adequate capability in larger numbers rather than perfect engineering in limited quantities that couldn't be replaced when lost in combat. The transformation represented more than technological adaptation to wartime necessity. It constituted fundamental philosophical evolution within German military thinking that acknowledged American approaches had strategic validity that German doctrine had dismissed as industrial incompetence. Engineers who had spent entire careers pursuing precision perfection were learning to accept adequate solutions that could be mass-produced and rapidly deployed to troops who needed equipment immediately rather than perfect weapons eventually. The bazooka had taught German industry that sometimes the best engineering solution involved not engineering for maximum performance, but rather accepting limitations while optimizing for variables traditional methodology ignored or considered irrelevant to weapon effectiveness. Combat reports from the Eastern Front provided final validation of American design philosophy that German engineers had initially dismissed as crude industrial shortcuts. Soviet 34 production had reached 2,000 units monthly by late 1943, overwhelming German technical superiority through numerical advantage that rendered individual weapon quality increasingly irrelevant to strategic outcomes. Individual German tanks remained superior to Soviet designs in armor protection, firepower, and mechanical precision that reflected superior engineering and manufacturing standards. But they were being systematically overwhelmed by adequate Soviet designs produced in quantities German industry could not match, while simultaneously supplying multiple fronts and replacing strategic bombing losses. The captured American bazooka had revealed uncomfortable truths that extended far beyond anti-tank warfare into fundamental questions about industrial strategy in total war conditions, where resource availability and production capacity often determined outcomes more than individual equipment superiority. German engineering excellence, famous throughout the world for precision and quality that set international standards, was being defeated by American mass production philosophy that treated military equipment as industrial products rather than precision instruments requiring specialized craftsmanship. The lesson would reshape post-war understanding of technological competition in modern warfare, where adequate solutions produced in overwhelming quantities consistently defeat perfect solutions produced in limited numbers, regardless of how superior those limited units might perform in controlled testing conditions. Koch closed his final analysis with observation that would influence military procurement philosophy for decades among nations studying lessons from the Second World War. In the end, we built a better bazooka that outperformed the American original in every measurable category of individual weapon effectiveness. The Americans built 634,569 adequate ones that equipped every infantry division in their global military deployments. Our engineering was superior. Their system was better. In industrial warfare, systems defeat weapons every time. The Panzerschreck entered widespread Wehrmacht service during 1944 as German forces retreated across multiple fronts under pressure from enemies, equipped with overwhelming material superiority. German infantry troops appreciated the weapon's increased lethality against heavy Allied armor, particularly against Soviet IS-2 tanks and American Sherman variants that were appearing in growing numbers. The 88mm warhead could defeat armor thicknesses that American bazookas struggled to penetrate, providing German infantry with capability to engage targets that would otherwise require direct support from increasingly scarce German armor or anti-tank guns. But the weapon's weight and complexity created persistent operational challenges that couldn't be eliminated through training or tactical procedures. The 20.3-pound loaded weight exhausted infantry troops during long approach marches that characterized German defensive operations. The blast shield and protective equipment requirements slowed deployment times when seconds mattered. The extended rocket motor burn revealed operator positions to enemy observation, creating tactical vulnerabilities that American bazooka teams avoided. German soldiers fighting with Panzerschrecks against American troops equipped with bazookas understood the irony better than staff officers analyzing statistics in Berlin headquarters. They were using heavier, more complex German versions of captured American weapons to fight the original American designs. German improvements had made the weapon more lethal but less practical for infantry operations, requiring tactical flexibility and rapid movement. By war's end, German factories had produced approximately 314,000 Panzerschrecks across all variants, a remarkable achievement under conditions of strategic bombing, resource shortages, and industrial collapse. The number represented German manufacturing capability operating under extraordinary constraints, while simultaneously producing tanks, aircraft, submarines, and countless other weapons systems needed across multiple fronts. American industry produced over 634,000 bazookas during the same period, while also manufacturing the world's largest fleet of heavy bombers, millions of vehicles, thousands of ships, and artillery pieces in quantities that dwarfed Axis production. The comparison illustrated fundamental differences between German precision manufacturing and American mass production that had shaped the war's outcome as much as any battlefield engagement. The Panzerschreck remained in service with various militaries into the 1960s, testament to the effectiveness of its basic design that German engineers had adapted from captured American weapons. But its legacy was more important than its service history. The weapon represented German engineering community's confrontation with American industrial philosophy that challenged fundamental assumptions about weapons development, manufacturing priorities, and the relationship between individual product quality and systemic effectiveness. Post-war German engineers, particularly those who would rebuild the nation's industrial base and create companies that would dominate global manufacturing in subsequent decades, learned lessons from the Panzerschreck program that shaped their approach to design and production. Superior individual products had value only if they could be manufactured in quantities sufficient to meet demand. Engineering excellence needed to serve strategic objectives, rather than pursuing technical perfection for its own sake. Sometimes accepting adequate performance to optimize production efficiency delivered better overall results than pursuing maximum capability, regardless of manufacturing constraints. The American Bazooka and German Panzerschreck told parallel stories about different approaches to solving the same tactical problem. Americans had asked how to give every infantry squad anti-tank capability using available industrial resources and existing workforce skills. Germans had asked how to build the most effective rocket launcher using their engineering expertise and precision manufacturing traditions. Both nations achieved their objectives within their respective frameworks. American bazookas equipped hundreds of thousands of soldiers with adequate anti-tank capability that changed infantry tactics and reduced dependence on specialized weapons crews. German Panzerschrecks provided superior performance that validated German engineering principles and gave Wehrmacht troops excellent equipment for engaging Allied armor. But in total warfare against enemies with superior industrial capacity, the American approach proved strategically superior through mathematics that no amount of individual weapon excellence could overcome. 634,000 adequate weapons distributed throughout entire military formations delivered more battlefield effectiveness than 314,000 superior weapons that couldn't equip every unit, requiring anti-tank capability. The lesson extended beyond weapons development into every aspect of modern industrial competition. Companies and nations that optimized for system effectiveness rather than individual product perfection consistently outperformed competitors who pursued technical excellence without considering production scalability, resource constraints, or strategic context. German engineers who dismissed the captured American bazooka as crude industrial work in February 1943 had learned by war's end that sometimes crude effectiveness defeats sophisticated elegance when strategic context includes factors beyond individual product performance. The captured American tube that Oberleutnant Richter examined in a Tunisian foxhole had taught German military-industrial complex lessons about modern warfare that would influence defense procurement philosophy for generations. Superior engineering applied to inferior strategic frameworks produces inferior results. Adequate solutions produced in overwhelming quantities defeat perfect solutions produced in limited numbers. Industrial systems matter more than individual weapons, and sometimes the side that asks different questions receives revolutionary answers that change how wars are fought and won. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.